Hello, my Calc BC kids. We're going to start Unit 9 today. The unit is on parametric equations and polar equations and some talk about vectors and relating the three things. So we're going to start with parametric equations, and this is something that some kids learn in pre-calc, but we don't necessarily do that from our school because they don't come up for a lot of kids. But for kids that are looking at Calc 2 or AP Calc BC, it's definitely a topic that's on the exam. So let me show you how it works. We've been looking at graphs of one equation with two variables, typically x's and y's. In the normal coordinate Cartesian plane, that's what we've always studied. But this is going to be now with three variables that are going to represent a curve that's in the plane. In the rectangular equation, we're able to determine where the object is located at a specific point, like an xy. But with the addition of a third variable, often t, we are able to determine when, because t usually represents time, when the object was at the point xy. So note the third variable t is oftentimes time, but not always. So we want to make note of that. And I'm also going to put a little note at the top that this is not the same thing as a three-dimensional situation where you have different planes like x, y, and z. It's not the same thing as that. Okay, so we want to make note that we're not looking at a three-dimensional situation. We're still looking at a two-dimensional situation, but we're adding a time factor or a third variable into it. Most of the time it is time, or t. So parametric equations. If f and g are continuous functions of t on an interval I, then the equations x equals f of t and y equals g of t are parametric equations, and t is the parameter. That's why they call them parametric equations. You can sketch the curve of a parametric by substituting in values for t. I posted a video on our classroom page that gives you, it's like an 8-minute video or so, that gives you an idea of what these things look like. The kids that I showed it to who watched it said it was really valuable in trying to understand what we're looking at right now. So I would recommend checking that out. If you can't get to the classroom page, then I got it on YouTube. So YouTube up Introduction of Parametric Equations, and you'll be able to find the same thing. So here's how it works. Sketch the curve with the following parameterization. Can I say that? I don't know. Where x of t is 2t and y of t is t squared minus 1, going between -1 and 2 for t. So all you're doing is you're going to take, your x equation. This one here, you're going to find x of -1. And you're going to find y of -1. And so you plug it in. I'm just looking at this very first box here. If I plug it in, I put a -1 in for t. 2 times -1 is -2. Go to the y equation. If I put a -1 in here, -1 squared is 1. 1 minus 1 is 0. That's my first coordinate. And so what I'm going to do is literally plot that coordinate on my graph, on my Cartesian graph here. So I go -2, 0. Here's my starting point. That's the very first point. And what you're going to do is go through and then plug in a -1/2, a 0, a 1/2, a 1, a 3/2, and a 2 into each of the equations just like we just did, and you're going to complete the chart. Now, for sake of our video time, I'm just going to tell you what these things are, and then we'll plot the points. Three 5/4, and the last one is 4 3. All right, so plot the points now. If I do that, -1, -3/4, these are estimations. 0, -1, 1, -3/4, 2, 0. Ooh, look at what it's looking like. Any thoughts? All right, if I connect it, I'm kind of looking parabolic, aren't I? Now here's the thing with parametric equations. Direction matters. Like where you start and where you stop is actually part of what you're looking at and evaluating these things. So what we do is we put little arrows along the way to say, oh, this point went to this point, and so forth down the line. You just put little arrows on there. So direction is important. So I'm going to make note of that over here. Direction matters. So use arrows. Okay. Direction matters. You want to use the arrows because they make a difference. The other thing I want to show you is how to do this on a calculator. Now we have a different calculator than what the curriculum video shows. So on our calculator, let me give you the notes on the side here, and then I'll show you how it works on the calculator itself. So the first thing you want to do is change the mode. Go to the mode button, hit the change the mode button to parametric. Okay, so this is on your calculator what you want to do. Change the mode to parametric, which makes sense because normally your calculator is in the function mode, and this is not a function. This is a parametric equation. And then you want to put the equations in. Put in equations. You want to adjust your window. And then you want to graph it. Now he gave you a window over here. We're not going to get too crazy technical with all of that, but let me show you how this thing works. So here is, can you see? I want to make it my calculator. All right, we'll try it out here. Oh, I have it in here. Hold on. So let me go home. So I want to hit the mode button. Mode button. The very first thing, normally, I'm going to change it back. Normally you're in function mode like this. So what you're going to do is hit the right arrow, and that gives you all your choices of the different types. Now we'll talk polar eventually too, but for now we're going to number 2, parametric. Press enter. And you have to press enter again, and then you're going to go to, so we changed the mode, now we're going to put in the equation, so you're going to y equals. And in the y equals, see how you have an xt1 and a yt1? You're going to put your 2 equations in there. So I have mine already in there. And literally you're using the variable t. T is kind of above the 9, a couple above the 9. So 2t and t squared minus 1, you put them in as your x1 and your y1. And then we want to adjust our window. So if I hit the window button, that's your green key in the F2. I know I want to go check your chart out. You're going with t values between -1 and 2, and really that's all I changed. Like I said on the note packet, he kind of gives you more things to look at, but this works for what we're trying to do. Just change your t min and your t max. We got that, and then we're going to graph it. And you can see there it is. That's our graph. So it started at -2, 0. And it ends at 4, 3. So that's how you graph parametrics. Now remember also to go back and change your mode back to the regular function because that's what we use 99% of the time. All right, so here we go. Next thing. To find a rectangular equation, now here's the thing, you want to put this, we want to know what this is equivalent to in a rectangular equation. We know what the parametric equations are, but I don't know what the rectangular, in other words, like what the y equals equation would be that would correlate with this picture. I can take a guess. Like we said, it looks a little like a parabola, so maybe it's going to be an x squared function of some sort, but I don't know exactly what the rest of it would be, what the rest of the dynamics of it would be. My guess is just that it would have an x squared in it. So here's what you do. To find a rectangular equation when you're given a parametric equation, you eliminate the parameter t by substituting. So this is going to be important to us. We're using substitution to be able to figure this out. And so here's how it works. I know that this means that x equals 2t. And I know that this is when y equals t squared minus 1. And so I look at those two equations, and I have to solve for t. That's what I'm going to do for this. I'm going to solve for t. Now I've got choices. I can either take this guy and solve for t, or this guy and solve for t, but I go for easy peasy lemon squeezy when I can. So this one is obviously the easier equation. And so I'm going to take that guy and I'm going to solve for t, which means I have to divide by 2. So I have x over 2 is equal to t. And then once I have that, I'm going to use substitution, that's a u, substitution, to be able to put it back into just x's and y's and get rid of the t, which is what I'm trying to do. So if I do that, I know that t equals x over 2. So let me plug it in, substitute. X over 2, t is x over 2, and I get this. And then I just, you know how these work with the AP exam, there could be so many different equivalent forms, but I'm going to pretty it up just a little bit. It would be x squared over 2 squared is 4 minus 1, or I could look at that as being 1/4 x squared minus 1. And that is the equation in the rectangular world. Now let's think if it makes sense. We know it's a parabola, an x squared. That's good. We know it's a positive x squared because see how it's a happy parabola. And I know it's a little fatter than usual because of the 1/4. And I know it's down 1 by the minus 1, which works for this. So it's fatter than usual, it's down 1, and it's a parabola. And so it all kind of fits together and makes sense. So you can switch between parametric equations, 2t, t squared minus 1, and turn it into a rectangular equation in your normal xy plane. All right, so here's another one like it. Given these parametric equations, 2 cosine of t and 2 sine of t, eliminate the parameters. Same exact thing, solve for t and substitute. And it's going to have a little kink to it though, as sometimes they do. So let's think. This is x equals 2 cosine of t. This is y equals 2 sine of t. Well, geez. Best I can do with these guys is to get the trig function with the t by itself. X over 2 cosine of t, y over 2 equals the sine of t. But I can't get to the t. If I were to substitute in, that's just not going to work for this one, right? So let's think about this for a second. We have to go back to a trig identity that you probably don't remember and wouldn't think to apply in here, but it's extremely important. And it's this guy here. We have a fact. We know the fact that the sine square of x plus the cosine squared of x, remember this Pythagorean identity, equals 1. And so I'm going to apply that to my situation right here. So that means I'm going to have the sine squared. Well, that's this guy. Sine of t is y over 2, so sine squared of t would be y over 2 squared plus. And I'm going to apply the same thing with the cosine. Cosine squared x, or in our case a t, is going to be x over 2 quantity squared, and that equals 1. Totally coming from this identity. I'm just using a fact. All right, now let's see if we can clean this up a little bit, just like we did in the one up above. This would be like y squared over 4 plus x squared over 4 equals 1. That would be another equivalent form. Or, interestingly enough, you could multiply everybody by 4, and it's going to be y squared plus x squared equals 4. Can you tell me about the graph of that? What's that a picture of? And if I think about it, I know that this guy is a circle, right? X squared plus y squared. I can say that it has a radius that is 2, the square root of 4. And I can say that it has a center. See how there's no numbers attached with your x's and y's, so the center's at 0, 0. And so I could graph that in our rectangular world by drawing a circle whose center is at 0 and the radius is 2 and connect it all together. And again, if you watch that introduction video I talked about that's on YouTube, they actually give you an example of that kind of a thing where they graph it that way. All right, that's the first page. Let's try the next page. We're going to apply some calculus to this now. So here's our next one. Derivatives, there we go. Derivatives of parametric equations. You knew you weren't going to get away from the calculus of it. So the derivative of a parametric equation is this. Given by x as f of t and y as g of t is found by, we call it dy over dx. And that would be the same thing. Now let's put the parameter of t in it. It'd be like dy over dt over dx over dt. Making note that this guy here can't be 0. Remember, you can't have a 0 denominator. So they kind of make note of that. Can't be 0. Dx over dt, that is. Now here's the easier way to think of it. This is the way that I think we're going to kind of apply it better. We want to take the derivative of the y equation and divide it by the derivative of the x equation. That's it. So y prime of t over x prime of t, that gives you the derivative, and there you go. So here we go. We're going to try it. Given x of t is t to the 1/2, y of t is 1/4 t squared minus 4. For t is greater than or equal to 0, find dy over dx. So we want to find dy over dx. Dy over dx equals. I need to have the derivative of this guy and the derivative of this guy. So maybe I go off to the side here and I figure out x prime of t. Well, the 1/2 comes down in front. I'm power ruling. T to the negative 1/2. Cool. For this guy here, I think I might distribute the 1/4 before I try to derivative, because otherwise it gets a little bit funky. So I'm going to say that this equals, maybe I'll go up above here, 1/4, I'll come here, y of t, I'm not derivativing yet, I'm just making y better, is 1/4 t squared minus 1/4 times 4 is 1, so that's sweet. So I can now y prime it. 2 comes down times 1/4 is 2/4, which is 1/2 t to 1 less power. So that's just going to be a t. There you go, 1/2 t. So let's put it together in our formula. I take the y of t, my 1/2 t. I divide it by my x prime of t, and that's my 1/2 t to the negative 1/2, and then I simplify it. Well, let's think about that for a minute. 1/2 times 1/2 over 1/2, they cancel each other out. So bye-bye, Mr. 1/2s. And then I'm left with a t to the first and a t to the negative 1/2 on the bottom. Do you remember the exponent rules? If I think exponent rules, I'm going to have a 1 minus a negative 1/2. I'm going to write it right here. This is t to the 1 minus a negative 1/2, which would be plus. So I get t to the 3/2. That, my friends, is your derivative. And really what you found, like any other derivative, is the slope of the tangent line. They're always one and the same thing. So speaking of tangent lines, right? Here I go, find the equation of the tangent line with number 5. So now I know what the slope is, how to find the slope. And you know that in order to figure out a tangent line, you need a slope and a point. So we're going to expand on this just a little bit. Let's go with the point. We know we need a point, and we know we need a slope to come up with the equation of any tangent line, regardless of parametric or what. So the point is your xy value, and they tell you when t equals pi over 2. So to find your point, you need to know what x of pi over 2 is, and you need to know what y of pi over 2 is. And that doesn't require any derivativing. Let's just plug it in. So these are going to be funky looking, but it's really not that bad. So x is e to the 2 times pi over 2. Well, 2 times pi over 2, 2's cancel, I get e to the pi. There's your x coordinate. Y of pi over 2, come over here, cosine of pi over 2. So, got to go to the old unit circle, think of pi over 2. Pi over 2 gives me the coordinate that is 0, 1. Cosine is the x value, and therefore it's 0. So I know I have a coordinate point where x is e to the pi and y is 0. So there's my point. Then I'm going to come over here and figure out the slope. Well, the slope is your derivative, which is what this is all about. So if I take the derivative, it is dy over dx So that is the derivative of y, derivative of cosine is negative sine. Derivative of x is e to the 2t times 2. So 2e to the 2t. All right, well, let's figure this out. Put in my pi over 2, negative sine of pi over 2 over 2e to the 2 times pi over 2. Sine of pi over 2, sine is the y value. I'm back over here with my coordinate. So it's a 1, but it's a negative 1 because of this negative. So I get a negative 1 on top, and on the bottom I get 2e to the pi. That's my slope. Now you can take it further, but we can leave it that way because that's going to give us an exact answer. So the question is, what's the tangent line? All right, we are y minus 0 from my point equals my m of negative 1 over 2e to the pi. And then it's times x minus e to the pi. There's a lot of equivalent forms you could see for this. Obviously, this could be just y equals yada yada. They could also distribute this through, and then you'd have the e to the pi kind of canceling out on the one side. But this is the answer, and that's good enough for where we're at. Notice that we really didn't take into account this t is greater than or equal to negative 1. That would come into play if we were trying to graph it. But we're not trying to graph it, so we're good with where we're at. All right, here's a couple that I want to play with our practice problems, and then we'll be done. First one I want to look at is number 1 because I thought it was kind of interesting. It brings in some logarithm rules that you may not remember. So that's kind of what I want to do with this. For the given parametric equations, eliminate the parameter and write the corresponding rectangular equation. Here's your x, here's your y. So eliminating the parameter, remember we did that as our first couple examples. You want to solve one of the equations for t and then substitute it into the other one. So we're going to take, obviously, the easiest of these two is this guy right here. So if I solve for t, see how t's in the exponent? I need to bring that t out of the exponent, and the only way I can do that is with logarithms. In this case, natural logarithms because it's an e. So here's what it would look like. I take the ln of both sides. That's what I'm going to do. So I have the ln of x equals negative t, it comes down, times the ln of e. Right? Take the natural log of both sides. But we know that the ln of e is just 1, so that just eliminates that. So now I've got a negative t equals the ln of x. So let me say it this way. T equals a negative ln of x. Right, I just move the negative to the other side. So I get t equals. So if I look at that, that really means this. This is the part that I didn't think you'd remember. That number in front, I'll write you a note here. Number in front, remember, is the power. And so what that really means is that you get t that equals the ln of x to the negative 1 or 1 over x. How about that? Now that's what you're going to substitute into the other equation. So here we go, direct substitution, y equals e to the 2 times the ln of 1 over x, and then I've got a minus 1. All of that is your power. Now this number in front that was over here that was your power, guess what? This 2 has the same effect. That 2 is actually the power on your x, and so here's what you end up with next. E to the ln of 1 over x squared, and then you've got the minus 1. Hopefully you're with me so far. Because here's the next blow your mind. What happens when you have an e and an ln? What do they do to each other? Hopefully you remember that they cancel each other out. They're inverses of each other. So here's your final rectangular equation, 1 over x squared minus 1, because the e and the ln cancel each other out. And so that's your story. That's number one. So hopefully you remembered some of the rules about those logarithms and such. Next one I thought was interesting was number 4, because it added something in that I wouldn't have necessarily thought about. A particle moves along this curve implicitly. xy plus y equals 9. If x is 2, dy over dt is 3, what's the value of dx over dt? So you know you have to derivative this, right? Because they were talking about dy's and dx's and such. So we know we have to derivative it. This first piece here is a product rule, x times y. So we're going to implicitly use the product rule on this. And here's what makes it different. We go the first times the derivative of the second, x times, now you can use y prime, you can use dy over dt, whatever you want. We're going to use dy over dt because that's the notation that they use. Remember, it would be 1, but you took the derivative of a y piece, so you have to say so. So you can either use a y prime, like we've done in class, you can use a dy over dt kind of thing. So that's what we're doing. And then product rule says plus the second times the derivative of the first. Well, the derivative of the first is the derivative of an x. Normally we don't say so, but with parametrics you want to say so, dx over dt. And then plus, now I'm here, the derivative of y is 1, but it's the derivative of y. And then the derivative of 9 is 0. And so ultimately what I'm trying to find is this piece right here, find dx over dt, right? What's the value of that? So they must have given us some information that we can fill in to be able to calculate that out. X is 2, cool, 2 times dy over dt is 3, plus, I don't know y, I don't know dx over dt, although that's what I'm trying to find, and I got a plus, dy over dt is 3, and this whole thing equals 0. So I'm just plugging in. Can you solve an equation with 2 unknowns? And you say, no, I can't. So there's got to be a way I can find y, because I'm trying to find ultimately dx over dt. So there must be something I can do to find this. If I go back to my original equation and I know that x is 2, you should be able to put the light bulb on there and calculate this out. I'm going to go up above. 2 times y plus y equals 9. 2y plus y equals 9. That gives me 3 y's are 9. So I know that y is 3, which lets me then say 2 times 3 is 6, plus 3 dx over dt, plus another 3 equals 0. I end up with 9 plus 3 dx over dt equals 0. Bring the 9 over, divide by 3. Dx over dt is negative 3. So what makes this one a little different than others is that when we take the derivative implicitly with parametrics of an x term, we need to say that. All right, let me see how many more I got. I got 2. I got 2 more to go. Here we are. Number 7 is next. This again brings about an interesting little thing, a little kink in the armor, the ones I pick. So 7 says a curve in the xy plane is defined by the parametric equations x is cosine of 3t, y is sine of 3t. What's the value of the square root of dx over dt squared plus dy over dt squared? Well, so let's go to this. Let's figure out what dx over dt is first. And then we can figure out what dy over dt is. And then we can put it into its square root form that they're asking me for. So derivative of the x function is the cosine of 3t. So derivative of cosine is negative sine. And it's going to be chain ruled times 3. So I get negative 3 sine of t, sine of 3t. And then I do the same thing over here. The derivative of sine is cosine. It's going to be times of 3, so it's going to be 3 cosine of t, 3t. Did it twice. Cool, so let's put it in the square root. See what it looks like. Square root, big guy. Oh, that's crooked. All right, I'm going to have negative 3 sine of 3t squared plus positive 3 cosine of 3t squared. Filled it in. Now I'm going to square it out a little bit. Okay, so if I square the negative 3, I get a 9. He's still inside. 9. If I square my trig function, this is going to be sine squared, but you don't square the angle. The angle just stays the angle. So that would be equivalent to 9 sine squared of 3t. This guy would be equivalent to 9 cosine squared of 3t. Well, that's kind of interesting. If I factor out a 9 and take the square root of 9, that puts me at a 3 on the outside. And that leaves me with a sine squared of 3t plus a cosine squared of 3t. Well, guess what? That fits an identity again. If I look at sine squared of 3t plus cosine squared of 3t, guess what it's equivalent to? Remember this from our first page? If you have a sine squared an angle, doesn't matter that the angle's 3t, it's just an angle, plus cosine squared of that same angle, then that whole ballywick equals 1. So here I am. I got the same situation. Guess what this whole thing equals? 1. The square root of 1 is 1, and 1 times 3 is 3, and that's your final answer. So how about that? Kind of interesting how that all comes into play. All right, here's the last one I want to look at, and that is number 13. So let me flip over to 13. And this one looks, let me read it to you, and you'll be like, what on earth is this asking? This is the easiest problem. But you wouldn't know that necessarily without thinking it through a little bit. Suppose a curve is given by these parametric equations, f of t, g of t, when t is greater than 1, and dy over dt equals t squared plus 2 over t minus 1 times dx over dt. What's the value of dy over dx when t is 2? Now remember, dy over dx from our very beginning when we put the definition of a derivative down was dy over dt over dx over dt. Remember that from our very foundation? So they're telling you what dy over dt equals. All right, so let me put it in here. T squared plus 2 over t minus 1 times dx over dt. Now that's my whole dy over dt. They didn't tell me anything about dx over dt, so that stays there. Now at this point you should have like light bulbs going off. Woo! This is really cool because guess what? I have things canceling. This whole hot mess there, I've got one in the numerator and one in the denominator. They can cancel. And so here's what I really have. T squared plus 2 over t minus 1 when t is 2. Ooh, 2 squared plus 2, 2 minus 1 gives me 6 over 1 or 6. How sweet was that? That is not normally the case when they give you all these values for dx's and dt's and dy's and dx's, and you know what I'm saying. So yeah, 6, that's it. All right, so you are to complete the rest of the practice problems, and I will see you in class with any questions, but email me if you need to. See you soon.